Hello and welcome to Trig Review. Yes, part 1. This is actually part 7 of our pre-calculus review. These few lectures, videos, whatever you want to call it, are going to be on trigonometry exclusively. So we already said that the right triangle is the one that has 90-degree angle, has hypotenuse and two legs. Some of the angles in the triangle is 180 degrees if the triangle is flat. And I neglected talking about angles. So we're going to start there, talking about angles, and then we're going to transition into trig and using, because we said that the trigonometric functions are functions that relate lengths of sides of the right triangle with angles of the triangle. So let's quickly, and I'll come back to all of this stuff, let's quickly talk about angles and the measurements of angles. So we have a point in space, and you can call that point A, and you draw two arrays out of that point. So these arrays are actually lines that extend infinitely through space. And we have this spatial separation here, which we call an angle. So now angle is measured, what we say, radially, right? So it's going to be measured this way. And the first angle that we are seeing here is having this particular measure. Now, it has nothing to do with the length of this line, because if I draw that line here, it's longer. If I draw it here, it's shorter, but this is still the same angle. It is the actual separation of the two rays, and that is fixed, so that's not allowed to move. It doesn't matter where you actually measure it. So now, the way we measure angle is either in degrees or in radians. If you're talking about degrees, I practiced the entire summer drawing these circles. So look, I'm actually master drawing circles. If you take this circle and you, from the center, you draw this line. It's like a positive x-axis, if you want to think about it that way. There is going to be going around, right, the circle. You make 360 divisions. So those divisions are actually each like a pizza slice. You know when you get a large pie and they're cut this way, you have 8 slices. So each one of these slices, right, is the same width if they cut it with a certain amount of OCD, right? And you have 8 of these slices. So you could have definition that the pizza has, well, 1 unit is sliced, so it's 8-slice pizza. That's actually, a pizza slice is a measure of it's a measure of an angle, because you can make that definition. What we are making definition here for degrees is that it's very, very tiny. This is way too big, but can't draw that small. This very, very tiny pizza slice here, we are going to call 1 degree. So what is 1 degree? 1 degree is 360th part of the full circle. That's what it is. So 1 degree, it is 1 with this little circle on top. So now, I mentioned earlier 90 degrees. 90 degrees is going to be, again, the circle that you have. And this circle is going to have 90 of these units. So if this is 90 degrees, that means there are 90 1-degree units. all together, one next to the other, and they create 90 degrees. And you can have any amount of degrees you want. We measure positive so you draw like the x-axis here. We measure positive angles counterclockwise and negative angles clockwise. So this motion is counterclockwise. Those of you who don't know what this means, there's a clock on the wall, right? Because you're used to digital clocks, right? So we have the old-fashioned clock right here. You can see that the second hand is moving, right, the way the, right, it kind of, now look at it's going through 1 and then 2, so it's going down on that side, and that is corresponding to the negative motion on this circle. So we measure negative degrees clockwise. For negative, and this is for positive angles. So now, when we construct a triangle, this triangle ABC is going to have 3 angles. There is the angle A, which is acute, meaning less than 90 degrees. He has angle B, also acute, oops, less than 90 degrees. And there is angle C, and I try to go for obtuse, which is larger than 90 degrees, and you have exactly 90 degrees, which is a right angle, which creates a right triangle. Now you can have all triangles to be acute. You can have one right angle or one obtuse angle. You can't have 2 of those because obviously they would add to 180 or more, and on a flat surface we cannot get that. Only on curved surfaces you can have more than 180 degrees. So now, or less. So now that you understand these angles, there is one more way to measure, and that is using radians. So another way to measure angles is to use radians. And now people will go, well, why? We already have degrees. Well, we also have feet and meters, right? So you have what, 2-3 countries using feet and then the rest is using meters. Is anyone switching? Yeah, I don't think so, right? So you have feet and meters, you have kilograms and pounds, even though pounds is not a unit of mass, it's a unit of force, but that's okay. We evolved to think of them as equivalent, they're not. So the only standard everywhere is time, right? We don't have anyone measuring in any other units than seconds, minutes, hours, days, weeks, years. So we all measure that. That's the only standard that we have. Everything else is all over the place. Even temperature. Freaked out when I landed to US first time. I didn't know about Fahrenheit. And the stewardess in the plane said, comfortable, landed at JFK, it's comfortable 83 degrees. I started panicking because I remember as a kid, I spent 2 hours outside at 42 degrees Celsius. I ended up in a hospital with sun poisoning for a week, getting some shot in my spine to survive. And I remember that horror as a kid. And then they said in the plane, comfortably 2 degrees. I said, I'm not leaving this plane. The hell? Right? So, different units. So that's exactly what's going to happen with radians and degrees. You are going to have the same angle measured in 2 different ways. And in some cases, you really want to use degrees. In others, you really want to use radians. Because they will measure the same angle, but they will have different numbers involved, and it's going to be much easier. Now, let's understand radians. They're a little bit esoteric. They're not the same as degrees. Degrees are kind of easy and lazy. So now, what are these radians? So you start with a radius here of a circle, and you say that the radius is equal to 1. All right? So radius is equal to 1. And then you have the perimeter of the circle, which you call the circumference of the circle. And you measure on that circumference length S equals 1. So that's the arc length. And I don't really care if you're doing this in inches or centimeters or meters or miles or kilometers, doesn't matter what. It just has to be 1 and 1. So when you have radius to be 1, and you measure 1 on the arch, this point has to fall somewhere. And this angle that you get here is then 1 radian. So 1 radian, right, is going to be the ratio of the S, which is the which in our case equal to 1 divided by the radius. And now you see that these radians are actually the weirdest thing ever. I didn't figure out this for some time. We call it 1 radian as a unit. But it's actually not a unit. If you had units over here, let's say in inches, and in inches, they canceled. Or if they were meters, they canceled. Or whatever you put. So if they cancel, then you actually don't have a unit. Right? But we call it radians. So it was very strange. It's like a unitless unit. Makes no sense. But then I understood that degrees is the same thing. Because you just take a full circle and you just divide it into 360 pieces. It's not really a unit. Like other things are, like meters and so on. But it's kind of interesting. Anyway. So now we understand that 1 radian is just a ratio of radius being 1 and the arc length being 1. When you measure it, you can use whatever units you want. And 1 divided by 1 is 1, so 1 radian. Now, we actually never use 1 or 2 radians or 3 radians as a measure of anything. We use divisions by pi. And now this is where the very interesting thing begins. At least in my opinion. Now you can have yours. So what I have here is what I'm going to call the unit circle. Because radius is 1. So unit circle and radius is 1. And I have over here 0. 0 radians. Now here are the divisions. If you go from one side to the other side, right, this being the center over here, this measurement we call pi. So half a circle is pi. And if you go the full circle, it's 2 pi. Does that make sense? Well, I would say hell yes, because we have that the circumference of the circle, right, would be 2 pi r, and r is 1, so you have 2 pi for s, and then if you want the theta for it for the full circle, it's 2 pi divided by the radius, which is 1, and you get 2 pi. So it is 2 pi to go all the way around. Now, if you draw the line up, and you know that corresponds to 90 degrees, this puppy on top is pi over 2, because it's half of pi. You went halfway from going the entire way around. And you have 3 pi over 2 on the bottom. And now you can get into this very interesting, well, actually, let's do that on the next one, much easier than here. So these are just some basic measurements. Now, if you want to think about degrees, you see that degrees for this particular application might not be the best way to measure things, because you work with 0, 90, 180, 270, and then 360. Do you really want to drag 270 through your calculations? Hopefully not. You know, 3/2 is much better than 270. 3/2 pi, but that pi is a constant that you just drag around. You don't actually compute pi, you just drag it around with you. So this radian measure provides much smaller numbers than what the degrees would show. Now, they're much harder to measure in terms of radians. So if you are an engineer, mechanical engineer or so, you are going to be married to degrees much more than radians. However, in mathematics, for purposes of calculation and general stuff, you want to use radians much more than degrees. So we are going to use degrees here and there, but primarily we use radians because it's much easier to compute. And then once you go to your physics courses, statics, dynamics, and all other courses that are heavily dependent on trig and angles and measurement, you will probably use degrees 99% of the time. Now let's see these divisions. Can you count? 1, 2, 3, 4, 5? You go with that? Then you should have no issues dividing. Oops. You should have no issues dividing circle using radians. So here's a circle. That's not a circle. That's a circle. I hope. What I'm going to do is I'm going to make the pizza slices now. Over here. Which will give me 8 slices. And I would like to label them with their radian measure, but also the degree measure. So degrees and radians together. So we start with the 0 radians. And we know that on top is pi over 2. Now, what's half of pi over 2? Well, clearly a quarter, right? So it seems that the pizza slice is pi over 4 in terms of radian measure. Now, I'm going to erase this pi over 2 from the top, which I used just to quickly come up with pi over 4. So, come on, pen, wake up. Battery? Maybe, I don't know. I'll try one more time. Go ahead. There we go. So I'm going to erase this pi over 2. I used it only for... and now look what I'm going to do, guys. Can you count 1, 2, 3, 4, 5? Let's count 1, 2, 3, 4, 5. So 0 pi over 4, 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4, 7 pi over 4, oops, and 8 pi over 4. Do you see that every single one that needs to reduce will reduce exactly to what we need from the previous circle? 2 pi over 4 is reduced to what? Pi over 2 on top. How about 4 pi over 4? Pi. How about 6 pi over 4? Yeah. And how about 8 pi over 4? 2 pi. Is that what we had before? Yes. It has to be. Otherwise, we broke mathematics. We go home and don't worry about it. You just have to count. 1, 2, 3, 4, 5, 6, 7, 8. You're done. Let's cut into... well, we can do kid slices, which is each slice in half, but generally we don't use those angles in math. So I'm going to use another cut over here. Hey, I'll draw a circle. There we go. So let me make another cut. So we go, again, these guys. But I'm going to cut each one of these in 2 places like this. OCD is very important here. Good morning. All right. So now we have these divisions. And you might go, well, how do I decide what's my first slice? We know here it's 0, but what's over here? Well, what you must know is that there is pi over here. All right? It's pi. So if this is pi, and you have 6 slices, exactly. I should call this one pi over 6, right? Can we make that to be the common sense? So I'll do it one more time. My question is, what is this? Is this a quarter, a third, a sixth, a 12th? What is it? Well, if this is pi, and we know it's pi because we learned it's a pi, right? When you have diagonal on the other side, and then you have 6 pieces over there. You have 6 pieces, so it's pi over 6. And I would really call that common sense. Now, count. Pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6, 6 pi over 6, 7 pi over 6, 8 pi over 6, 9 pi over 6, 10 pi over 6, 11 pi over 6, and 12 pi over 6. 12 pi over 6 is 2 pi. It landed right at 0, full circle. I know that these divisions are perfect because, with the numbers, because I counted all the integers, didn't skip any. And when I went all the way around the circle, just like with my pi over 4s up there, I ended up at 0 with 2 pi when you reduce. And now you reduce all of these, and you get what we call a unit circle with values that you will need to know for your trig course. So now I'm going to draw a new circle where I'm going to just copy these numbers, but these numbers are going to be reduced. Now, the way I copy might be a little bit, different than the way you copy things, but that's okay. I'm done, by the way. So now I'm going to replace all of these. So 2 pi over 6 is going to be pi over 3. This puppy over here is pi over 2. This reduces to 2 pi over 3. This stays pi over 6. Here's our pi, exactly where it's supposed to be. 7 pi over 6 stays, but then 8 pi becomes, right? 8 pi over 6 becomes 4 pi over 3. 9 pi over 6 becomes 3 pi over 2. 5 pi over 3. 11 pi over 6. And finally, at 0, we get 2 pi. So 0 and 2 pi share the same location. Reduce fractions. So this is the one that you are studying and learning. So now, is there an equivalent in degrees? And the answer is yes, right? You just draw a new circle. See? Quick. You draw a new circle, and then you replace all of the values with degree values. So the only thing that you actually want to know, well, first of all, you know 12 pi over 6 is 360, right? Degrees. Half of 360 degrees on the other side is going to be 180 degrees because that's half. You already know that on top is 90 degrees because that's the 90 degrees is the right angle. Now, pi over 6. Well, if pi was 180, 180 divided by 6 is 30 degrees. And then as soon as you know that this is 30 degrees, you can just keep adding increments of 30 around. Because each of these pizza slices is the same in terms of the angle. So if from 0 to 30 is 30 degrees, then from 30 to the next one is 30 degrees. So 30 times 2 is 60 degrees. And then you see another 30 gives you 90. So that's good, right? And you can just keep going around adding 30. So 30, 60, 90, 120, 150, 180, 210, 240. Here's our check. 240 plus 30 is 270. 300 and 330. Plus 30 is 360. We end up right where we need. So the same unit circle given in degrees, do we want to use it? No, we don't want to use it in degrees. Because 360 and 330. And I don't want to use 330 if I can use, you know, the 11 pi over 6. It's much smaller numbers. So easier to deal with if we are using radian measure. But degree measure is there. And now we get to this very important conversion. And the conversion says that pi radians is equal to 180 degrees. Now you have to use units, radians and degrees. I developed very severe allergies when someone says, "Oh, pi is 180 degrees." Hell no! Pi is 3.14. That's what pi is. Pi is not 180 degrees. Pi radians is 180 degrees. Pi is 3.14. So you have to make sure that you know. So pi is approximately 3.14 and has nothing to do with angles. Pi is a number, just like your E was a number, about 2.7. Has nothing to do with the angles. E has nothing to do with angles. Pi has nothing to do with angles. Those are just numbers. Pi radians is a measurement. Now, pi is important because it divides our unit circle perfectly. So we measure circle and angles in radians in terms of pi because that irrational number pi is the one that gives us nice divisions. But pi is not by itself, right? It's used, but it's not itself. Angle. So that's the introduction to angles. Well, there's more. So now the question is, can we have more than 360 degrees and more than 2 pi? And the answer is yes. So can you have, let's say, 475 degrees? Does that make sense? And the answer is yes, it does make sense, and you can have it, but it's more than one revolution around the circle. Your engine in a car has thousands of revolutions per second, per minute. It's called the RPM of the engine, right? Revolutions per minute. And they say 1,000, 2,000, 3,000, right? 8,000, red line already, right? So you can have more than one revolution. So what is 475? So 475 is going to be a full circle of 360 degrees plus 115 degrees extra. So this means in a circle, when you start at your 0, and you know that there is 90 on top, you will make, well, maybe we can draw the whole thing. There we go. So you will make a full circle, and then you will go extra past 90 degrees to this location here, which would be 475 degrees. So full circle is 360 to go around the circle, and then you go extra, and you get to 475. Now what's interesting is, see, 475 degrees is not the same as 115 degrees, but it's at the same location in space. And there is something that it's a little bit freakish. But I will remind you, what's the day today, all day? Anyone knows? No, the day.
Oh, the day?
Day. Thursday. Was there a Thursday before? And hopefully there will be one next week, right? So, does that freak you out? No. You know that there were Thursdays, for as long as you were alive, there were Thursdays. There were Thursdays before you were even born, right? For thousands of years, there were Thursdays. And hopefully there will be Thursdays for thousands to go. So that's called periodic behavior, right? You go to buy food periodically. You don't live in a food store just getting the stuff off of the shelf, right? You go to the store once or twice a week and get stuff. So there are certain things you periodically get gas for your car. So there are these things that you do periodically in life, and this is that type of a behavior. So if you want to think about a 115 being a Thursday today, then 475 is a Thursday next week. That's actually what it means. it's a very interesting thing. Now, I'll give you another example, but don't do this because it's a ticket. And don't ask me how I know. If you have a circle, traffic circle like the one in Somerville, Flemington, whatever, right? And you have 4 streets coming in. You come in on one street, and let's say this is your exit. You go around the circle and you exit. Right? No, you don't go other way. I said don't do this. You can go in a circle, go 5 times around, and then take the exit. It's a ticket, by the way. So, would you agree that you entered on the same street and took the same exit off of the circle? Yeah, right? Now, whether you went 3/4 way, which is, right, 2 pi over 3 pi over 2 radians, 270 degrees, or you went 5 times through the circle and then took the same exit, right? Spatially, right, space-wise, it doesn't matter. Time-wise, gas-wise, ticket-wise, and all other things, it doesn't matter, right? Plus, you really don't want to stay in a circle for longer than you absolutely must, especially the one in Somerville. I mean, it's a death trap every time. I think there are more car parts lying around that circle than in any of the car stores around. Right, so that's technically what it is. So now I can talk about any size of the angle, positive or negative. You can give me any number you can possibly think of, and I'm going to come up with amount of, so give me a 3-digit number, anyone. 214 was first. What was yours? 267. I like her better because it's 7 at the end. 267. I was about to say, give me a 3-digit number, which is odd, but I didn't get to finish. You guys jumped in, but I was looking for the odd one. And then I'm going to put pi, and then I'm going to put 6 on the bottom. Clearly, this is angle given in radian measure, right? So this is radian. So now you have 267 pi radian. How many full circles do you have in 267 radian? How would you figure that out? That's half circles. If you divide by 6, you... Oh, times by 2. Well, how about just divide by 12 and call it a day? So this is the part where you look at the denominator, right? And you see a 6 there. Now you know it's a 2 pi for the full circle. So if this is a 6, 2 pi is 12 pi over 6. And that's the full circle in 1 over 6 units, right? If this is a 4, it would be 8 pi over 4. Whatever denominator is, it's double to give you the full circle base. So now you clearly see, hopefully, there I say clearly, that you are supposed to divide 12 into 267. You get 2, it's a 24, it's another 27, it's another 2, 24, and you are left with 3. So what do you have? You have 267 pi over 6 is equal to 22 full circles, right? So this is a 22 full circles, and then you can call this revolutions. So 22 revolutions. You go 22 times around the circle before you take exit. And what's the leftover? The leftover is 3 over 12, which is a 1/4. 1/4 of a circle, which is 3 pi over 2. Yeah. No. And then plus, 3 over 12 of a full circle. Now 3 over 12 is 1/4 of the full circle, which is 90 degrees, which is pi over 2 radians. So what do you have? You have 22 revolutions. And this, so this is equivalent. This whole thing, 267 pi over 6, is equivalent. I don't want to put equal. It's not the same as pi over 2, but it's in the same location, right? So it reduces to pi over 2, if I did my calculations correctly. So let's see, 12 into this goes 24 times 2 is 2, and then 7, and then this, and then 3, and 3 over 12 left. So 3/12 of a full circle, and 3/12 it's 1/4, and then 1/4 of a full circle is pi over 2, and yeah, pi over 2. So there we go. So it's 22 full circles, and then 90 degree on top. If you want to graph that, you will have to go 22 times around, and then that pi over 2 on top. Yes?
Question. When you do like the little pizza pie, right?
Uh-huh.
What happens if you get like 3 on top and 4 on the bottom?
3 on...
You ever run a solution like that? Like
Yeah.
There's 3 slices.
Uh-oh.
Slices in the bottom.
We have a syncing issue here, so we lost all of these numbers. I have to put them back. I'll have to actually write your. Let me just fill this in. Oops. 2 pi over 3, so that's 6. So this is 5 pi over 6, 7 pi over 6, 4 pi over 3, 5 pi over 3, and then 11 pi over 6, and finally 2 pi. Let me draw the circle now and answer your question regarding. So this is a circle, and I will draw the halves. Now, what happened? What was your question?
What I'm saying is, let's say in the bottom there's 4 slices, right? Like the bottom half.
Yes.
We always have
4 slices, yes, because it has to be, the pizza slice width has to be the same.
Okay.
Because, see, all of these are straight lines through the origin.
Mm-hmm.
So when I draw the straight line through the origin like this, if it cut in 2 places here, it will cut on the 2 places on the other side.
So it will always have to go through the origin.
It has to go through the origin, and you can't have 3 slices up or 3 slices. You can make 7 slices, but they're not going to arrange themselves nicely. So, you know, like Mercedes sign,
Yep.
like this, right? Well, that's fine. We can do this.
Mm-hmm.
But it's, you know, so we'll actually have to turn the Mercedes sign on the side to fit our 0 situation. But this is okay, because from here to here is 2 pi over 3, and this is 1 pi over 3 over there, and no, 2 pi over 3 over there, and 4 pi over 3 over here. There we go, and then this is 2 pi. So Mercedes sign still can be made, right?
Mm-hmm.
We don't have the other pieces, but this is cutting the circle in 3 equal places, 3 equal spots. So the requirement of the unit circle is to cut it with the same size slices, right? This is what my pizza slice looks like. Boom, done. It's 2 pi. Like 4 pi, but.
The problem that we just did, when you said 22 full circles and pi over 2 to the radian. That one. Now, if we were putting this in radian form, it would be 22 full pi over 2. And if we were doing this in the degrees, when you do 22 full circles, 90 degrees.
Let's address that.
Or when you put
let's write. Yep. So what was the number 267?
Yes.
So 267 pi over 6 radians. Now, I said that this is equal to 22 full circles. Now, 22 full circles is actually, one circle is 2 pi, so this is 44 pi. And then plus pi over 2 in radians. So this is the measure that you would write in radians. So 22 full circles is 44 pi, because 22 times 2, right? Each one circle is 2 pi, so you have 22 full circles. It's 22 times 2 pi is 44 pi. So that's for the full circles. And then the leftover would be pi over 2. So that's an extra 90 degrees to make it to 267 over 6. So this is what we have for that one. Now, you can transfer this into degrees by going 22 times 360 plus 90, right? Now, some students would be interested in just the straight conversion, especially engineers, mechanical engineers would be interested in converting this into degrees directly. The 267 pi over 6 radians. Now, the way you convert this is, and technically you'll see this conversion in chemistry all the time, not with degrees, but with other units. You put the unit you want to cancel on the bottom, and you put the unit you want to keep on top. Because radian will cancel radian. That's why you put it on the bottom. And now, obviously, 180 is associated with degrees, and pi is associated with radians. That's the way you deal with conversions. So now, observe that pi kills pi, radian kills radian, and you are left with 267 times 180 divided by 6 degrees. Now, luckily, 180 and 6 cancel down to 30, so all we have to do is 267 times 3 and add a 0, right? So 3 times 7 is 21, and then 18 and 2 is 20, and then 6 and 9 is 8, and add a 0 at the end. So this is 8,010 degrees to convert 267 pi. Now, if you are to divide this number by 360, right, which I'm taking the calculator now because I'm lazy, 810 divided by 360 degrees must land to 22.25, because 90 degrees is a quarter of the full circle. If you are dividing 8,010 degrees by 360, which is full circle, you're getting 22 full circles, and then a quarter of a circle, which is 90 degrees, and that's exactly what I have, 22.25, and that 0.25 is a quarter, that extra 90 that you had to go. Now see, the interesting thing here is that your calculations can be done in one or the other unit, right? You can do it in radians, you can do it in degrees, but I still stick with radians because this is 8,000 and this 267. So radian measure will always have smaller numbers for calculations, and you drag this pi around than degrees. Now, will I have anything against if you do it in degrees? Hell no. Go ahead, right? But all of the later calculations in calculus become much easier if you are accustomed to radians rather than degrees. So this is what we have in terms of measuring angles. Once we understand measuring angles, once we understand that the angles are different but the location in space is the same, when you go the full circle and you end up at the same location, like Thursday to Thursday, or think of a month, the same thing, right? Months. Oh, by the way, sometimes I do this to, when we deal with these numbers, is to just give you the circle, standard circle that we had so far, same units and same divisions. And then just you can put on it, but you have to start here. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and then there's your 12. That's your clock, but as you can see, it's backwards, and it starts at where the 3 would be on a regular clock, because that's where we start measuring angles from the x-axis. Guys, remember that all of this is going to live eventually on xy axis, so that's why we start there. Unless you're dealing with bearings, but bearings will be doing that as a clock because it's north. Bearings for ships and stuff, so they want to do north to be the main axis. But we'll deal with that when we get there. What else can I do here? Can I do January, February, right? I can do that as well, and I can go. So you have to understand the cycles. So what does it mean? Year and a half, right? Year and a half is going to be the full year of 12 months, an additional 6 months. Now you're again in June, right? So whether it's going to be 6 months and then it's June, or a year and 6 months and it's June again, 2 years and 6 months again June, it's June, 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 June. Doesn't matter how many times you go the full year around. If you are going this extra 6 months, you always land in June. If you go extra 9 months, you always land in September, and so on. So there is a big difference between 2017 and 2018. But March is March. And there is a March in 2017, which you can think of 3. And there is a March in 2018, which you can think of full year, plus 3, which would be 15 in that case, right? But they're same location. You are in the same spot. So periodicity is important. And we are going to actually use that in trig to reduce our calculations. So now I'm going back to basic trig measurements, and I am going to give you values between the length or size of the triangle, right, the ratios, and the numbers that you can get, the angles and all of that stuff. So you might know already that sine of 30 degrees is 1/2. You might also know that sine of pi over 6, which is 30 degrees, is 1/2. So this is two different ways of writing the same thing, one in terms of degrees, one in terms of radians. And what we do here is, so sine 30 is 1/2, and then, now you say, well, how do you know that? Well, I know this because of the unit circle. If I draw a unit circle, I can do this calculation in the unit circle. And the numbers work out that way. So if I have my standard unit circle, and I need 30 degrees, so I'm going to chop it up on 30 degrees like this. So this is the standard circle. And now, what I'm considering is 0 to 30 degrees. Now, I get to drop this vertical over here. I know that this is on the xy axis, so this is x going all the way, this is y going all the way. And I know this is 1 because it's a unit circle. Let me erase this 0. So this is 1 on the x-axis, 1 on the y-axis. And I have this triangle. Now, sine was defined, sine of the angle, sine of angle A, whatever. Sine of angle A is opposite over hypotenuse. Now, you already see that the hypotenuse over here is 1, because that's the radius of the circle. When you consider this triangle, 90 degrees is right here. I don't know if you see this, so here you go. Much better. So the little triangle over here, when I drop this, I'm going to drop the vertical from scratch. So this is just a standard unit circle, 30 degrees, we're all happy. It's a unit circle, which means from the center to any point on the circumference unit is 1. So what is to be the hypotenuse of our triangle is 1, and what is to be the bottom side of our triangle is 1. And now I drop the vertical from the top to create the triangle, and there's my 90 degrees, and this is my angle A, which I am considering. So now, I know that the sine is defined. This is what we did last time. I have to scroll all the way up to this, where we said that what you must memorize, the sine is opposite over hypotenuse. Opposite is the opposite of the angle, and hypotenuse is the longest side. So now, going back to our triangle, observe that the line that is on the x-axis is not 1. See, it comes short here. Right there where I drew the line is short. You see this little piece over here that I kind of put in a little. So the sine on the bottom is shorter. Sine on the bottom is shorter. So the longest side, the hypotenuse, is actually the side where the 30 degrees is, which is 1. That's the hypotenuse. So we plug that 1 for the hypotenuse. And then this guy, when you read its value on the y-axis, is 1/2. And it turns out to be that the sine of 30 degrees is 1/2 divided by 1, which is 1/2. Now, do you actually go and remember the way to get it? No. You remember values. You remember that tangent of pi over 4 is 1. You remember that the sine of 60 degrees is √3 over 2. You remember that the cosine of 60 degrees is 1/2. That's what you remember. Now you say, what? What do I remember? Yeah, you remember those values. Now those values are extremely easy to remember if you like remembering numbers, or you can remember the way to write them in about 20 seconds, depending on what you, because some of you are visual learners. So here is the way to know values of trig functions quickly. Guys, if you don't have a calculator, you can just cry, right? So pay attention. I'm going to put just the important stuff, and then we'll talk about reference angles and all other things, and it will be easier for you to come up with these values. So what are the important numbers? 0, 30 degrees, 45 degrees, 60 degrees, and 90 degrees. The rest doesn't matter. We have sine, cosine, and tangent. We know that the other three are flips, so it's easy to flip these values. Now, I know you can go back and watch the video, but I'm still going to ask you to put your pens and pencils on the table and stare at the screen. You will write this quickly. It is the procedure that you need to see and remember, and the life will be very easy after that. Ready? So pens and pencils on the table, eyes to the screen 100% of the time. Look at this. Let's count together. 0, 1, 2, 3, 4. Divide by 4 everywhere. And take the square root of the whole thing. And you're done. So, to find all trig values for these angles, you must set it up 0, 30, 45, 60, 90, which are actually the only ones that we care about. And then you simply count 0, 1, 2, 3, 4 divided by 4 and take a square root. When you compute these square roots, the values for trig, for sine, all come up. And you will see your sine 30 is 1/2. So let's take these square roots. Well, 0 divided by 4 is 0. Square root of 0 is 0. Square root of 1 is 1. Square root of 4 is 2. There's your sine of 30 is 1/2. Then you have 45 degrees, where square root of 2 you cannot take. But square root of 4 is 2. So this is root 2 over 2. Square root of 3 you cannot take. And here's your root 3 over 2, which I mentioned earlier. And probably some of you freaked out. And now 4 divided by 4 is 1. Square root of 1 is 1. What's sine of 45? Root 2 over 2. What's sine of 90? Sine of 90 is 1, right? So sine of 90 degrees is 1. Sine of 30 degrees is 1/2. Sine of 0 is 0. Sine of 45 is root 2 over 2. Right? Goes like that. So my students write this chart. Obviously, none of this is given for any of the exams. And knowing this in Calculus 1, especially Calculus 2, if you have to go, and I know engineers do have to go, and computer science has to go to Calc 2. Trigonometric integrals, trigonometric substitution, polar coordinates, parametric equations, the whole trig. You don't know this stuff sitting in Calc 1 and Calc 2? Sheesh. Now, it's going to be stumbling and slow in the beginning when you learn it for the first time. Everything is. But the more you practice, the better off you get. And then, right, students who are sitting in, those classes, they pick these values up. They don't think about it because they know it. But you have to start somewhere. So we know how to obtain values for sine. You know for cosine? Same values, write them backwards. 0 goes here, 1/2 goes here, root 2 has to align, root 3 goes there, and 1 goes here. So for cosine, they're exactly backwards. Same values, just backwards. Now, the first identity that you will learn is that tangent theta is sine theta divided by cosine theta. So if tangent is sine divided by cosine, then the tangent values better be when you divide 0 by 1 and you get 0. Divide 1/2 by root 3 over 2 and you get root 3 divided by 3. Root 2 divided by 2 divided by root 2 divided by 2 is 1, because you are dividing same numbers. I don't care how much root 2 divided by 2 is. I'm dividing it by itself, so it has to be 1. Root 3 over 2 divided by 1/2 is just root 3, because 2's will cancel. Can you divide by 0? Undefined. And we are going to see quickly that there is a vertical asymptote there, so undefined makes sense. Every time you divide by 0, there's a vertical asymptote lurking. So now we have these values. What's tangent of pi over 6? Looking at the chart. Now you go, what the hell is my pi over 6? Well, pi over 6 is equivalent to what in degrees? (30). Pi over 2 is 90. Pi over 6 is 30. Now, is there an easy way to get these pi over things easy? You know that 90 is pi over 2, right? So this is the way the pi's work. You start at 90 and you go 2, 3, 4, skip 5, 6. I don't know if that helps, but 2, 3, 4, skip 5, 6. You know that 90 is pi over 2, so 2, 3, 4, skip 5, 6. Pi over. What's tangent of pi over 6? No. What's the tangent of pi over 6? Root 3 over 3. Yeah. So, sine of an angle is going to give us a number. Put that one on the cloud. Sine of the angle gives us a number. Angle can be given in degrees. Angle can be given in radians. So tangent of pi over 6, you use your eyes, you look at the chart, and so on. Used to have competitions for my students. See who can, from scratch, white paper, nothing on it. How fast can you write this chart out? So go ahead, try to beat 18 seconds. 18 seconds, I said. Yeah, some people actually practice that because it's fun and they want to win. Well, yeah, you're either a winner or a loser. What? Is that a foreign concept to you? Yeah, there you go. There's no in between, and all of that stuff. You know, a trophy for a last place. You know, for the little team who didn't make the cut. It goes really quickly away as soon as you graduate. So yeah, 400 applicants, 1 position open. Is there a trophy for the second place? Oh, there's a job for the first one in line at 399. Out from scratch. It's the way it works. Yeah. So 18 seconds. Go ahead, try to beat that. Try to beat 18 seconds. So in the beginning, it will take some time for you to learn how to construct the table. And in time, as you use this a lot, you know, cosine of pi over 6 will become root 3 over 2 naturally. Tangent of pi over 4 is going to become 1 because pi over 4 becomes 45 degrees quickly. So all of these things go fast. Now the next part is, well, the chart didn't address the other ones. Yeah, I know. There is no secant of pi over 3 on this chart. So what is secant of pi over 3? And can we calculate secant of pi over 3? Because you will have to calculate that secant of pi over 3 in calculus. So secant of pi over 3. Well, we said earlier, if you go back to our basic chart over here, that the secant and cosine are flips of each other. You see, cosine is adjacent over hypotenuse, which is what we did yesterday. Now look down there. Secant is hypotenuse over adjacent. So, if secant is pi over 3, I can do 1 over cosine pi over 3. Now, that would be 1 over 1/2, which is 2. Now, this is the standard way of dealing with those three that are not in the chart, because they're flips. Don't say inverses. They're not inverses. They're just flips, okay? You swap domain and range, and that's it. That's not domain, wow. Denominator and numerator. For inverses, you swap domain and range. So we're going to have 6 trigonometric functions and 6 inverse trigonometric functions. So there is going to be the inverse secant function and inverse cotangent function. So these are not, secant is not inverse of cosine. Hell no. Inverse cosine is inverse of cosine. So we're going to have 12 functions altogether. 6 regular and 6 inverses. Now the regular 6 functions are paired in 2 groups. A group of basic sine, cosine, tangent, and then the flips of sine, cosine, and tangent, which are cosecant, secant, and cotangent. So that's what we have. So now, the other way to deal with the secant of pi over 3 is to go and say, well, if cosine of pi over 3 is equal to 1/2, then the secant of pi over 3 has to be 2 over 1, which is the flip, which is just 2. So you can deal with this either saying that the secant is 1 over cosine. Cosine of pi over 3 is 1/2. 1 divided by 1/2 is 2, which I would say is a safer and conventional way, and so on. Or you can just use the common sense and say secant pi over 3, well, secant is connected to cosine, so if cosine of pi over 3 is 1/2, the secant is a flip. Because remember what the cosine is. Cosine is adjacent over hypotenuse. Secant is hypotenuse over adjacent. So you get to flip this thing. So on that note, I'm going to ask you to figure out the cotangent of pi over 3. The cotangent of pi over 3. Today, while we're still young. So the fastest way to deal with this is to say tangent of pi over 3 is root 3. Therefore, cotangent is 1 over root 3. And then we rationalize. We don't like root 3 in the denominator. So root 3 over 3. Are we clear on that? So let's stop here for the break. When we come back, we're going to calculate these values for any angle in a galaxy. So we're going to take your 267 pi over 6 and calculate sine, cosine, and tangent for it. So we'll have more. I'm going to stop the stream and then we'll resume. So